Hello, Assalamualaikum warahmatullahi wabarakatuh, and welcome to another session of EPO 640 Electric Drive. So for this lecture session, we will be discussing on part 3 of the AC drive, that is the voltage to frequency control. So if we look back at the previous lecture that we had, we already discussed on how to derive the torque. Okay, so the torque expression using the small slip approximation. So from the small slip approximation, the value of the torque value, we can drive our AC motor within several parameters that we have discussed before. Okay, that is the pole changing, visualized by the P. Okay, and then we have the rotor. Okay, rotor resistance control by changing the value of R. The line voltage control by changing the value of V1, and also the line frequency control by changing the frequency. Okay. So for this lecture session, we will be discussing on the control schemes. That is the scalar vector control, and particularly the V2F, okay, voltage to frequency control. And for these control variables, you have we will be looking into the line voltage control and the frequency control. Okay, because we are talking about V2F, so both we will look into the voltage and also the frequency control. So for converters, okay, now we are use modern control. They're using power electronics to control their both voltage and frequency. Okay, so what are the types of converters, modern converters, that we can use in order to change or increase or decrease the voltage and frequency? So first we can look into the cycloconverters. Okay, so cycloconverters are using control rectifier. Okay, so in the for the cycloconverter, you can control both the appropriate voltage, okay, and the appropriate frequency that is controlled by the firing unit. Okay, with if you put in the desired speed, the desired values, okay, and of course to put on the limits. Okay, so another method is to use two-phase two-stage converters. Okay, so two-stage converters with a DC link. So first you have the rectifier circuit. So rectifier circuit will dictate the supply voltage, okay, by triggering the firing unit, okay, firing angle for the voltage. And after setting through the DC link and go through the inverter part, okay, where the inverter will invert from DC to AC with the help of the PWM scheme, okay, PWM controllers. So this is also, you can if you're dealing with the DC, okay, DC input, so also you can imagine it as a battery bank, okay, and the output of the DC will be fed into the AC, which is the inverter, and okay, it will be controlled by the PWM controller. So the induction motor, okay, so for induction motor, it requires a three-phase AC voltage source, and depending on the supply voltage, okay, so the AC DC AC converter, okay, so if your supply voltage is AC, so the AC DC AC converter with DC link can be used to provide the three-phase AC voltage supply to the induction motor for variable speed control. So the control rectifier converts the AC supply to DC on the DC link, and the PWM inverter converts the DC voltage on the DC link into AC for the induction motor with, okay, so with variable voltage and variable frequency. So both can be controlled, okay, by the inverter, okay, also, okay. So but the rectifier only controls the voltage, okay. And the speed and torque control can be achieved using, okay, both scalar control and vector control, okay. So first we will be looking into the scalar control. That is the voltage to frequency, V to F. So having looking at the effects of increasing your frequency, okay. So with this you can see your torque to speed, okay, graph here. So you have for example for okay, frequency F1 higher than frequency 2, frequency 3, and so on. So for the higher the frequency, okay, it increases the no load speed, okay. So okay, no load speed, for example here you have your no load speed here, okay, for F1, okay. So you have, sorry, this one is the torque, so no load speed will be here, okay. So this one will be F1, okay. And so you have increase in no load speed, but you have the decrease in the your maximum torque, okay, here. So the decrease also, you have decrease in your starting torque, okay, and increase in the speed at the starting, okay. You have increased speed in the starting, okay, but decrease in the starting current, okay. So that will be the effects of the frequency, okay, by changing the frequency. So again, if we look at the equation, okay, okay, assume the sinusoidal AC supply and neglecting the VR stator. So you can see that you have a significant you have this relationship between your voltage and the frequency, okay. So so the increase of frequency, your air gap flux and your rotor current decreases, okay. And by reducing the frequency, the air gap flux increases, and continual increment in result, you have a flux saturation and excessive stator current and distortion of flux wave, okay. And that's why we need to have a constant V to F, okay. So if the rotor frequency is kept constant, okay, so the torque developed by an induction machine is proportional to the square of the flux in the air gap, okay. So so this can be proven, okay. So by deriving the maximum, okay, so deriving the torque, okay, and derive it when you have your maximum torque occurs, when your dt over df is equal to 0, okay. So if you derive this, you will get your maximum torque, okay. So the torque here, so the maximum torque, okay, so based on the equation of the maximum torque, it varies between the supply voltage, okay, supply voltage and the frequency. And to achieve a constant maximum rated torque at a variable speed and high efficiency, so both the supply voltage and supply frequency should vary at a fixed ratio, okay. And this we can look into the for example, for the two-phase converter. Okay, you have at the base frequency. Okay, the machine terminal voltage is at the maximum and can be obtained from the inverter. So both the frequency base. Okay, so below the frequency base. Okay, below the frequency base, you have the air gap flux is maintained constant. Okay, by changing of the V with respect to the value of F. Okay, so hence we can maintain the maximum torque. But if we look into increasing the base frequency, if we change the frequency higher than the base frequency, so voltage cannot be further increased. Okay, and the air gap flux decreases with F increases. Okay, so in corresponding to field mechanic control, so this is what we call the field mechanic control of a DC motor. And if we look at in V equal, okay, in the equation of V equal K omega, so K is such that the rated voltage occurs at the rated, okay, base frequency of 50 Hertz. So if voltage is at maximum voltage, okay, so the field must be reduced if we wish to increase the speed. Okay, that's for if you have a in the region of constant torque. But however, the power and hence the motor current must not exceed the rated values. Okay, and if you look at the control loop for the V2 frequency control, okay, so this is the open loop control, and you can see that here you set the VA, the V, and here you set the frequency. Okay, so of course this is the process where you want to keep the ratio of good ratio of V to F. Okay, so this is an open loop system, and of course if we want to control the speed, okay, so the open loop of the VF control is not sufficient. So there must be a sensor, speed sensor at your rotor, at your load, and the speed must be measured and compared with the set value in order to be controlled. So you have a different using a for example this is a PI, okay, PI controller, okay, to compare. Okay, this comparator, either summer or compare. Okay, compare with the current speed of the machine. Okay, so compare with the speed that you want. Okay, and then this will be fed to the controller, PWM controller, that detects the switching signal for your inverter. Okay, and this is the frequency. Okay, so this is a step function for the slip frequency control. Okay, so okay, step function equation, and the unity gain feedback. Okay. So the value of SDC can further be okay, changed to A. Okay, and so it's the same equation. Okay, so okay, so the speed error given by the difference between the speed and the rotor speed. Okay, set speed, okay, speed that's been set, and the rotor speed at the first cycle. Okay, cycle represents the slip frequency, and slip frequency is processed through a PI controller to produce speed SL, and at the second cycle, okay, the set slip frequency, speed as omega SL is added to the rotor frequency in order to generate the stator frequency. So omega SL is typically kept at low value to achieve higher efficiency. So for this, the slip frequency as a control variable. Okay. So at the linear range of a torque speed curve, you can say that torque is proportional to the omega slip. Okay. And this will be done in the controller. Okay. So this will be the controller will provide the firing angle, okay, to the power converter and so on. Okay. So control units are to control the input of the power converter to match the load and the motor, and it can be implemented with either analog or digital. Okay. So in digital circuits, the control algorithm may be implemented in either hardware. Okay, so for example, ASICs or FPGAs, okay, or software, that is the microprocessors or microcontrollers or digital signal processors. Okay. So advantages of a digital control circuit. Okay, for example, DSPs, FPGAs, it enables complex control schemes for a better speed to torque ratio or value. So enables smoother starting, and it's more efficient and has efficient control for braking and reversing. Okay. So other types of control system, you have open loop control. It's simple to implement, and also you have the closed loop control, and it's more accurate, and it has a better response and steady state accuracy. So for more reading in this topic, you can check your textbook, okay, and also you can check all the supplementary additional references, additional in your notes. Okay. So with that, thank you and have a nice day.